Good afternoon, everyone. Can you hear me?
Yes.
Okay, great. Okay. So we're just going to be half of the class in this revision class because the Friday lab group will be having theirs on Friday. And so we'll be looking at assignment 4 and 5 today. Okay. Yeah, 4 and 5. So the assignment 6 is more of the examples in our test. I just wanted to be sure we all went through the examples. Then assignment 7 and 8, I'll be doing a video of the solution for those two assignments and I'll post it on Moodle over the reading week. And once I post on Moodle as well, I'll send an email to everyone or make an announcement for everybody to know that the video is up. Okay. And then
That'd be great, yeah.
The reason why I didn't have to make this solution like a slide, like the last two solutions, because some of us we are yet to turn in our solution for assignment 5. So if I have to put it up on Moodle, for those who have submitted, they will be shortchanging them because those of you that have not submitted will quickly run through your solution with what we have, then make changes, which will not be the right thing, okay? So that is why we just have to, I'll just display then take it off, okay? But by Friday, after the Friday class, when everybody must have submitted the assignment 4 and 5, then we can put the video up, put the solution up, and then put the solution for, I think by Friday, all the assignment apart from 7 will be due, right? So I expect that.
I think so.
Yeah. So I expect that everything will be with me. Then I can put up the solution to help us better prepare for the midterm 2. Okay. Then the midterm 1 that we did, I have before we look at this, the class today will just be 1 hour, like I said. But I want to make a comment on the first midterm we did. If I was to be very strict on the kind of screening process, we sent the criteria for the test, and we also sent the way you should act, the details of what is expected. But most of us did not, maybe because we didn't have to emphasize it. I don't know. You were meant to be able to show your desk at least with both hands and on it and your paper. But most of us did not follow that. We're just showing our face like I am doing now. I had to chat some of us, call out our name, but we still did not adjust. Ideally, or should be receiving an email, for those of us that displayed that saying your test has been canceled, you have to retake it or something. Please avoid that in this second one, okay? So that we'll not have to do that. So permitted us or let everything slide in the first one because it's about our very first. But for this second test, please don't do that. If you don't have the right setup, come to school to write it in person. Or if you don't have the right setup, go to the library. We'll have several things that can help you or several ideal environment that can help us, okay? Please. All right. That being said, if we have any objection, I also said we said you should not turn off your mic or camera. Some of you did at interval. I was supposed to immediately I see your camera off or your sound off, eject you from the hall. I could, I could admit and eject from the hall, but I didn't do that. I didn't have to do that because I just assume, okay, so our first, let's let everything slide. But the second one will not be. I'm not saying in essence that we're strict, very strict, but just comply, okay? Okay, so assignment 4 says we should solve problem 1, 4, 5, 6, 7, 8, and 25. If you have the assignment on your system, you can quickly open it up so that you can read alongside as we are revising it, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8 questions to look at for assignment 4. Short solution questions and answers. So let's begin with the first. Now, the very first question will have a picture representation of someone in the car, the first image and the second set of image. Now, this question said we should, from this figure, we should show the sequence of the head and neck motion for the passenger in an auto accident. Which one correspond to the head-on collision and which one correspond to the rear end collision? Then you should explain your answer. Now, this is just another way we can ask instead of just saying define Newton's law, Newton's second law, or conservation law, or something. We present a scenario and expect you to know that this scenario actually applies to this particular law. Okay, and that is why we added the word explain. Now, with this motion of the person, if we look at the head at the beginning, we see, sorry, I'm looking for my pen. Okay. So we see this is before the heat, right? And the person experienced a heat. We see that this one, the neck went back, and then this one, the neck went forward. So the one that went back, you know that the heat came from the back, and the front one is the head on, okay? So the rear end is A, and the B is the head on collision. Now, what law does this explain? This explains the Newton's first law. You remember the dummy image that we used in the first case where it crashed into the wall? The person tend to continue in his motion until the force at the wheel stopped it, okay? So I just put a brief explanation here because I expect diversity in the choice of words, that is expression in different ways, not hook, line, and sinker of what I put up here. So that is why I just limited it here, just to just buttress that After picking that the image A says rear end collision and image B says head-on collision, you should go further to explain the reason by using the whole process to explain the law of motion that applies to this. You see, when the first law emphasized that, which is like the law of inertia. Some of us we just say it is the law, Newton's law of inertia, that says an object will continue in a state of rest or at a state of motion at a constant speed on a straight line until it is acted upon by an external force. And I use the word ETC to say that you can keep elaborating on your answer, okay? Because it's an open-ended answer saying you should explain. So we'll look out for keywords. Your ability to state, introduce that an external force will act on the system will be at rest or in continuous motion, and then the use of some keywords like constant speed, okay? So that is kind of answer I'm expecting from us. If the question we give does not expressly say this, which it can be another kind of analogy to express another law or definite statement in physics. Okay, so that is that for number one. So move on to the next one. Do we have any question on that one?
Nope, sounds good.
Thank you. So the second question says we should use the picture to answer question 1 to 6. And what are we meant to do? We should show we have two forces presented. We should redraw the diagram and add a third force that makes the resultant force to be 0. We should draw another vector diagram, introduce a third force such that the resultant force of that system is 0. Okay, so the new force we are going to add is not the resultant force, but we should label it as force 3. Okay, so pick the first one. We have the first image F1, F2. Where will the F3 be such that the total or the resultant of the system will be 0? Same applies to this and this. Okay, remember when we were treating this, we did one class example, something that looks like this, number 4 question. Okay, so to get our third force, we first of all took the resultant of 1 and 2. So F1 plus F2 gave us that. So we now look for the third force such that the third force will make this resultant to be 0, because the resultant of this and the third force should give us a net force of 0. So we have to draw another force of equal magnitude to that one in opposite direction. So that's how we got this one. So if we apply the same idea to this one.
I have a question.
Okay.
For the first one, wouldn't the arrow be pointing in the other direction, like more similar to the second? Because otherwise it would still continue going to the left there. Shouldn't it counteract the force, like the force going to the left by going to the right?
It's going to counter this resultant force.
Okay.
Yes. So it will counter this resultant. That will make the total force on that system to be 0. If it goes in another direction, that is, it's not going to be countering the resultant force.
Okay, thanks.
Okay, so in the same way, when we look at these two forces, the resultant for this force, the magnitude of the F of the one is greater than 2, so this motion went in the direction of the resultant force. So the resultant force motion is going upward. Therefore, the third force that will counter that will point in the opposite direction. Okay, that is, will balance the force that will balance the force upward, such that the total force of that system, net force, becomes 0, have to point downward. So it pointed downward such that F2 plus F3 was equal to F1 for number 5. Okay, so we use the same idea. We get the resultant, then get the third force that will counter that resultant. That's what we've done in 4, 5, and that's what we did in 6 as well. So we got the resultant of these two, which will be here, and then we'll have the counter force as F3. Okay, so we have the diagram in this form. All right, I'm still going to put this whole solution like slide, then make it a video lecture like I did in the last one I put up on Moodle. Okay, so that explains question 4, 5, and 6. We try to explain how we got it. This is just like an explanation of what I just said. So when we have the summation of the total force of that system, the net force should be 0. So let's move on to question 7. Anytime you have a question or a comment, just raise your hand or come to the mic and we'll hear you out, okay? Ideally, the way the revision class is supposed to be, if it was in person, is meant to be such that we'll pick up any question, one person comes to the board, solve it for us, everybody make comment, we'll say our idea. Is not going to be like the instructor talking and it's like I'm teaching. It's more like another teaching section. Okay. So the number 7 says a girl is swinging on a rope. We should identify the forces acting on the girl at the very top of her swing. Okay. They specify that we should identify the forces acting on the girl at the very top. Okay. When the girl is at the top, the force acting on the girl is the force of gravity by the ground. Okay. This one is, in our textbook, we have solution of odd numbers, but we don't have the solution for even numbers. And in solving this, some of our assignment, we see also that the values for the solution does not tally exactly sometimes. Some varies with some few digits. Okay. So
Would you be able to say that when she's at the top of the swing, that she's basically in free fall?
when she's at the top of the spring, if she does not hold on to the swing, if anything happens, if it's going to, the force that is going to pull is going to go, yes, like you said, free fall motion.
Okay, thanks.
Okay, so that is why we said that the force acting at the top on the girl is the free fall.
So that's why you kind of feel like you're floating a little bit, like when you hit the very top.
Yes, the pull of gravity is very strong at the very top. So you feel weightless. We will also see in our second example how that feel of weightlessness comes when we start talking about apparent weight.
Okay, thanks.
You're welcome. Does any other person have comments? We can always add to our explanation, not just force of gravity by the ground. Okay, we can buttress on our reason or our answer response with few more words, just to emphasize our understanding of why we picked the choice, the force of gravity. Okay. All right. So question 8, you are exploring a cave, then standing in a low cavern. You steady yourself by pushing straight up on the rock ceiling. Identify the force acting on you. Okay. So most of the assignment parts for this assignment 4 is just touching briefly every aspect of chapter 4. Okay. So we talked about the law, and then we identified the forces. So let's see if you're in the cave. We just did like a picture diagram. To identify that force, we just did a free body diagram showing the person in the cave. When the person stood upward, we see the direction arrow pointing like 3 forces. So we'll have the normal force that will be acting on that person. That's the normal force of contact with the base or where the person is standing on that cave. So the person stood upright. So we'll have the force, the normal reaction force acting due to the bottom pointing up. Opposite, normal force will always be opposite to the contact of surface. Remember when we talked about catalog of forces and how we can identify their direction. So we'll have also the force due to gravity that will be acting on that person, which is weight. Okay. Then we'll have another force that will be acting on that person, which is the force on that force acted by the ceiling on that person. If you can imagine the cave, like you're in a cave, such that when you stand, in some of the solution video online, you will see that the person was able to touch the ceiling, but in some of the solution video, the person did not really actually touch the ceiling. So we'll have the direction of the force, weight force, but on the person and the normal force. But if, because I've gone through some of our solution, we're able to identify this and this have the least mark, okay? So you are about 70% to the solution. All right. So the question 25, I think we've covered so much that I got a mail, somebody was asking me, how is the exam going to look like? If you check the breakdown of your courses, if you've been doing all your assignments, participating in class, you're already more than halfway into your score. So you don't have to say, oh, this is too voluminous. How do I memorize so much? Okay, just take it one step at a time and you'll see that it's going to be simple. So let's see the 25th question. A 55 kg ice skater is sliding along at 3.5 meters per second, which is its velocity, and this is its mass. So 5 seconds later, our speed dropped to, what happened? Sorry. 5 seconds later our speed dropped to 2.9 meters per second. The question is, what is the magnitude of the kinetic friction acting on her skates? Okay, we know that kinetic friction, one of the forces we have discussed, and note the word magnitude. Okay, it means that even if your answer is negative, our emphasis is not really on the signs. All right, but the signs will help you to arrive at the right answer. So we use the Newton's second law, which is F equal to ma, and we know that our a is actually change in velocity. So to get the magnitude of the kinetic friction, which is the force acting on caskets, we have to impute the value here. The same thing I have here is what I just wrote out loudly so that we can see it. Okay, so we'll have the final, which is 2.9 minus the initial over the change in time, which is 5 seconds, times the mass. So we got 6 points, that's negative 6.6 Newton, but the question says magnitude, so that is how our answer became 6.6 Newton. Okay, which some of us also, most of us got it correctly, only very few left their answer in a negative sign. And that's because maybe they did not remember the emphasis of magnitude. Okay. So I think this is the last for this first set. 46. So we use jet expulsion for rapid escape. You know this sea, let's say sea fish or animal, I don't know what to call it, but it's like a fish. What it does is, we use when we're treating Newton's third law and we're emphasizing action and reaction pairs, we use the snake neck turtle as an example, where the snake neck turtle have to take in water and then use the water taken in to accelerate the neck region to hit a prey. The same kind of scenario is what the squid does. It will take in water rapidly to accelerate away from position. So it just jets out so fast. It does it so fast so that you should just go to YouTube if you have free time. Just put the motion of the squid. You enjoy the speed, the kind of life that animal, or the kind of way the animal moves. So that is the idea this question is asking. It uses jet expulsion propulsion for rapid escape. So the squid pulls into its body and then pulls in water into his body and then rapidly eject the water backward to propel itself forward, to move, to accelerate away from its position. So we now want to analyze that motion. A 1.5 kg squid, which is the weight of the squid fish, not including the mass of the water, don't this emphasis, can accelerate, sorry, this is squared, okay, 20 meters per second squared, which is acceleration, by ejecting, this is the mass of water, 0.15 kilogram of water. So we have the mass of the squid without water, we have the mass of the water, and we have the speed that it can achieve if it takes in that volume of water and ejects such volume of water. So the question is, what is the magnitude of the thrust force of the squid? What is the magnitude? Again, note that word, magnitude. Signs are important, but when they ask you about magnitude, signs will not be relevant, even when your answers are negative or, yeah, because if it's positive, you don't put the sign, you are still right. But if it's negative, you have to put the sign. But when the emphasis is on magnitude, you don't need the sign. So what is the magnitude of the force on the water ejected? The C part, what acceleration is expected by the water? So we have first the thrust force, secondly, the force being the magnitude of the force of the water being ejected, then thirdly, the acceleration. They gave us one acceleration before, so what will be the acceleration for the water? Okay. So let's see the solution. This is not so clear. So we'll have the mass of the squid 1.5 kg. We'll have the acceleration, which is 20 meters per second squared. And we'll have the mass of water that was given to us. All these parameters are already stated in the question. The first question is, what is the magnitude of the thrust force? If we apply Newton's second law to that, thrust force is equal to MA. We have the magnitude of the thrust force for this squid. Okay, just want to be sure we saw that so that we would not see it for the water. So 1.5 times 20. If you do that, let me see, what would that give me? 1.5 times 20 give us 30 Newton. And then the second question says, what is the magnitude of the force of the water being ejected? Okay. Because we've already said the whole movement of the squid uses the principle of the Newton's third law, which is the action-reaction pair. We know that if we know the particular magnitude of one towards the other direction, the opposing direction is going to be the reaction pair of equal magnitude. Okay, so they both will have the same magnitude, but the signs will be different to point that they are going in different direction. But the question is emphasizing the word magnitude, not the sign. So that is how we didn't have to do any further calculation. We just explain. So in this kind of question also, you have to be able, don't just say 30. You have to also explain that this is actually the application of the Newton's third law, the action-reaction pair, and this is how you choose the figure 30 to be your answer. So if you just say 30 Newton, fine, you got the value, but without this, if it's a multi-choice question, you might probably see just 30. But if it's not a multi-choice question, if you have to write it out, don't be tired to write everything you think you should put down. Okay? Don't reserve some answers to yourself. You don't need that reserved answer. Point it out. All right, to earn your full mark. Okay. So we'll have the second one to be 30. And then the final question says, what acceleration is experienced by the water? So for the water, we know the magnitude of the force. And for the water, the mass of the water was given. So the acceleration experienced by the water is mass of, we also use this. Then we made A the subject of formula to have A equal to F over MA. That's how we got this. Okay. So the mass of the water was given to us in the question to be 1.5. So that's why we use 1.5 here to get the acceleration of the water ejected. Okay. Do we have any comment on solution? We've all submitted assignment 4, I think. Yes, it's long due, but I still have some persons who have not done in their assignment. Okay, so I'm going to share.
Sounds good.
Thank you. I'm going to share the question for assignment 5. We have, the class is 1 hour. We'll have just a few minutes to go through that. Okay. Can you see my screen?
Yep.
Okay, so for this, I'm going to be, if you have the question 5, if you have it written out, because the question 5 is not, the solution is not way down like it is in question 4. I just put, I'm yet to like type the solution or write it like I did in. And the reason, like I said in the first case, is because I don't want to have to display so much. For those of us who have not submitted, we can change our answers. But for those who have submitted, we'll be shortchanging them, which is not right. So we'll just do like a quick rundown and I'll be displaying another screen. If I touch a different screen, do you see the different screen? There's a way to sync on my screen. I don't know how to do that. Can you see the slide I'm showing now? No.
We see the Word document.
Just the word, okay. Okay, so if we need the second screen, I'll just unshare this one to share that. So if you have access to your textbook, you can open your textbook so that we'll read out the question. You'll not be distracted with the share and unsharing of screen. So the assignment 5 says we should answer how many, total of how many questions? We'll have 1, 2, 3, 4, and 5. Okay. Total of 5 questions, 20, 21, 29, 30, and 31. So let's start with the very first, 20.
Sorry, just to clarify, this is the assignment that's due this week, correct?
Yes, on Friday the 5th.
Okay, and this is the only one that's due? We don't have assignment 8 due this week?
Assignment 8 is due also on the 5th. I think I put the due date on that. When I uploaded a Moodle, the due date is on it, right? It's only assignment 7 that I did not put the due date. Assignment, yeah, 7. That's the only one without the due date.
Okay, so this Friday you do want both 5 and 8 then?
Yes.
Okay, thank you.
Thank you. So the first question says, and I actually wanted to do just solution 1, but for Friday we'll be doing 4 and 5. So if I don't do the 5, because some persons have not submitted, I'll be shortchanging those in class for Wednesday. But at the end, by revision week, I'll be putting up the video for the solution for 4, 5, 6, the 7. I'm not sure what I'll do about that, but because it will be captured also in the test, maybe I have to put it up, but you still have to turn it in. Okay. So the riders on the power tower are launched skyward with an acceleration of 4g, after which they experience a period of free fall. What is a 60 kg rider apparent weight? So the person is 60 kg, and then the apparent weight during, we're asked to look for apparent weight, we're looking for both apparent weight during launch and during the period of free fall. Okay, so the question gave us two information: the weight of the rider and the acceleration of the rider. And if we remember our discussion on apparent weight, we talked about apparent weight in relation to the description of the contact forces. You remember that we said the apparent weight, that feeling of lightness or heaviness during motion. Okay, and that feeling actually comes by being in contact with certain surfaces. So apparent weight is always related to N, which is the contact or normal force. Okay, so we'll have the information given to us as 4g, which means that the person is feeling like it's 4 times heavier than the weight of gravitational pull on that person. All right, so let's picture in our test, we see the picture of that riders on tower. They are sitting down around the tower, they launch them upward, then they allow them to experience free fall down. Okay. Okay, so before the ride, the person is at rest. The person is not making motion. They put everybody at rest, get to ensure safety, put on your seatbelt and all that. No distance is covered, no initial velocity, and no acceleration. Okay. The total force on the y axis is 0. So at that point, the normal force and the weight force, everything is just equal because that body is at static equilibrium at that point. But immediately the ride is launched, the person is going up and is going to be feeling heavy, right? It's going to be feeling heavy. It's going up. No, it's going up. It's going to be feeling, when it's dropping, it's going to be feeling, it's going to be on a free fall motion. It's for the lift that when it's coming down, you feel the weight on the floor. When it's going up, yeah, you feel heavy because your weight is acting against the motion. So we'll have the acceleration, which is 4g, which means 4 times the acceleration due to gravity on that person. So 4 times 9.8 gave us 39.2. Okay, so we try to do a free body diagram. The weight is still minus, but we see the vector line for the normal force being higher because the direction of the net force is actually upward. So acceleration goes in the direction of the net force. So we have the net force on the y-axis being Fy equal to ma. Okay, so the information given to us is that the person is going to be feeling 4 times heavier, but the question is what is going to be its apparent weight. So we have the net force and then the weight, which is going to be acting in the downward direction to equate the total force on the object. So we have this summation of forces on the y plane, which is this and this, will give us ma. So we have that expression N minus mg equal to ma. So the apparent weight, which we defined as that like the force of N, If you remember the formula or the definition for apparent weight, the contact force. You see the contact force in this system is just a normal force, which is N. So apparent weight is going to be equal to N. So hence we have to determine N to get our apparent weight. So from this equation, all the parameters are already provided. We have the mass. We can actually cancel, then make N the subject of the formula, but we just went first by substituting before making N the subject of formula. Okay, so M is 60, G is 9.8, M is 60, and acceleration as given is 39.2. So we'll have move this one, subtract this from this, or add when this one crosses, is going to be add. We'll add this to this to get 294 Newton as the apparent weight when it launches upward. Okay, so what is going to be its apparent weight when it's experiencing a free fall? Theoretically, we know what happens during free fall. The person feels weightless, right? The person is not really feeling. Sometimes, even if the person is in contact with some object, because that object and that person is also experiencing the free fall, it's only when the person is about to stop, that object's about to stop, that you feel that heavy weight again on that object. So we also, during free fall, try to do the free body diagram. The free fall, the motion, the net force point in this direction because the force of gravity. So we see the vector length of the arrow representing the free fall being longer than that. So the net force direction is downward and the object is heading downward and the pull of gravity is acting on that object. So we'll have the total force expression also being equal to MA, but we'll have Fy being actively minus mg. So in the first case, we had our force being MA, but because it's the force of gravity, our MA is actually mg, which is also mg. So if you move this to this side, or even if you substitute the values, you see that this will become plus. So you have minus mg plus mg, giving you 0 Newton. Now the essence of the value 0 Newton is that feeling of weightlessness. Does not mean the person does not have weight at all, but its apparent weight during free fall, which we theoretically know that when an object is on free fall, it's going to be experiencing kind of weightlessness. Okay, so this agrees actually with the theory of free fall and apparent weight. Okay, do we have question on this? Can we proceed?
Sounds good.
Thank you. So we'll have the question 21, still on apparent weight. Okay, so we're just going to read the question, then I'll share another slide or a different screen, or try to write on this screen. Let me make it bigger. Okay, so we have Zach, whose mass is 80 kg. Is in an elevator descending at, this is the velocity, the speed of the elevator, because we see its direction is down. Sorry. So the elevator takes 3 seconds to brake to stop at the first floor. What is Zach's apparent weight before the elevator starts braking. We're also asking Zach's apparent weight while the elevator is braking. Okay. In our textbook, I noticed that the solution value was given to us as 780 Newton and 1100 Newton. But when I calculated it, I was not getting 780 Newton. I don't know. I also saw some solution. Some persons just wrote approximately 780 Newton. And I understand because the textbook said 780 Newton. So I expect the contribution of those of you who got exactly 780 Newton. If you have maybe a reason to share with the class, well, how you got the exact 780 Newton, because I did not. I tried using G to be 10. I still did not get 780. Okay. So how many of us here in the class got exactly 780 Newton? Can I see your hand raised? Or we have not submitted? Say in the chat yes or no. Did you get 780? Okay. Okay. Okay, so I got 784, but some person said they got exactly 780. So I like to learn also, how did you get your 780, please? If you got 780 and you are willing to share, can you please come to the mic and let us
Yes,
know?
I can share.
Okay.
So I times the mass by the acceleration by gravity. That gives 784, but the question only, like, isn't it just one sig fig? Wouldn't you round, like two sig figs, wouldn't you round down to 780 if you go by sig fig rules? That's what I did anyway.
Okay, great. So now I agree if I go by sig fig rules, I'm going to get 780, and everybody in the class agrees to that. Great. But my confusion was the textbook did not emphasize anywhere, and the question did not emphasize anywhere that we should keep our value in 2 sig fig. And in the question, I know if we go by the sig fig rule, majorly we apply that to experiments, not really solving question in class like this. Okay, so for those of you who presented and gave the reason, which I saw in some of the review for those, some persons did not say the reason as 6 fig, they just put approximately 780. And I was just wondering, okay, how did 784 approximate to 780 without any comments? All right. So I agree with those that use the 6 fig to get the 780. And then for those that got the other value as well, we all have our right answers, and the right score will be given to that. Okay, so apparently we all will be on the same page now. And somebody's making comment, technically goes to 800 since there's only one sig fig. Yeah, that is exactly what I was thinking. The question has one sig fig, and then I think it's only this one. This one is also one sig fig, but that's a drilling, 2 sig fig. So the question has just majorly one sig fig, and if we express that, it will be 800. Some solution actually, when you view them on YouTube, got 800, and they use the sig fig rule. And some also use 10 as their G, and they got value higher than what we have. So the variation of these answers comes when we don't state that you should use G as 9.8. Sometimes we state that on your formula sheet, we just put G 9.8. Sometimes we can put G 10. If we put on the formula sheet G 9.8 and we want you to use G to be 10 in the question, we will specify in that question that you should take G to be 10, okay? So in the case where we did not specify that, you should use the G value on the formula sheet, okay? So let's see what we did to solving this apparent weight problem. We just use the same principle that we know about the formula for apparent weight, that will have the normal force and the weight force acting on it. So the summation of the normal force and the weight force acting on that system, summation is 0. So the normal force is actually going to be weight, which is mg, which is the ZAC times 9.8, and we got 784, which when you go by the 6-week rule, 780 Newton. As the answer, this is the answer you see in the textbook. Okay, this is the answer I got. So if you explain that this is 6 feet, then we proceed. But for the benefit of everyone, I will stop the mark here. Okay, so for the second one, I also had the same challenge. The answer in our textbook was 1100, but when I solved, I was having something way different, far from 1100. Okay, so how many of us also got 1100? Okay. Yeah, I have a comment. The person said, since G is 2 6 feet, then we can leave our answer in 2 6 feet. Okay. G is 2 6 feet. It's possible. That's the idea. But when the question did not give us details or instruction on the 6 feet to leave our answers on, it's best to use the value obtained. Okay. Okay, so for the second part of that question, which is the apparent weight while Zach came to while the elevator was braking, how I solved that, and I'm still seeing comment. If you still have comment about this, quickly, let's say that, let's proceed. Okay, doesn't matter. So for the second part, let me wipe off this part. The question says, what is Zach's apparent weight while the elevator is braking? So while the elevator is braking, Jack is going to experience also a kind of heaviness because it's beginning, the elevator is stopping, so his weight is resting more on the contact surface. Okay, so we'll have also the variation in its contact force value. All right, so we have that the initial velocity, which is heading down, was given to us as VI, which is minus because it's down. The direction was seen descending, And then it's going to stop. Our final velocity is going to be 0 because the motion is coming to a stop. Okay. And our change in time was given to us as 3 seconds. So we'll have V final, V initial change in time, and mass in all the parameters given. So we use this motion equation, F final equal to F initial plus acceleration change in T. So if we substitute the values that we have to be 0 minus 10 A3 or 3A, whichever one we call it. So we will have 10 being equal to 3A. Okay, which will now make our A to be equal to 10 over 3, which will give us 3.3333 to infinity. Okay, so we'll have 3.3 meter per second squared. So now that we've obtained the value for acceleration, we can actually use our equation for the net force of the system being equal to MA, which is equal to the normal force minus the weight for the apparent weight. And we know that W is mg. Okay. So we now have MA being equal to N minus mg. Okay. So the mass of Zach is given to us to be what? 80. We can choose to make N the subject of formula directly before solving, or substitute the value, then solve for N. So, but what you're actually looking for is N to give us the normal weight. So 80 times 3.3, then we'll have 3.3, which is A, being equal to your N. Sorry, is this one clear? Times that N 89.8. So if we move this across, we're going to be adding MA and MG to give us N. Okay. So in the end, I got the value 9491048 Newton. But the answer in the textbook says 100 Newton. I don't have explanation for this. Does anyone have that can help us in the class now? Comment on this, please. Yeah. Did we have a different answer? Did we get 1100 Newton, 1100 Newton? Because if you do the 2-6 fig rule, this does not approximate to 1. This approximate to 1, or did you approximate to this, approximate to this to get this? Do we have comment, or we should just proceed? Okay. Okay, got 105.4, 107. Okay. Okay. So another thing I want to say is that most times when we mark theory questions, the emphasis is usually not at the final point, we tend to distribute the marks on the process, okay? So if you're having marks that are a little different from the final, sometimes we use plus or minus range. So it's possible your value will be within the plus or minus range, okay? So is that all the comment we have about this? Okay, let's proceed to the solution 29. We have now some of these questions. Sometimes when you read the test, you see some questions that says 1, 2, 2 in the order of trick or energy needed to solve the questions. Sometimes we just limit ourselves to 1 and 2, but we just bring in 3 because sometimes some of the solution to 3 that's actually straightforward, but a little bit tricky as well. Okay, so solution 29. Hold on, let me go to my solution 29. Okay. 29, I think this is the last one, so we should be done in the next few minutes. And if you have any reason to exit the class, just let me know and I can excuse you. Okay. So it went back to the beginning. Question 29. In question 29, we have that a 1,000 kilogram car traveling at a speed of 40 Newton. Sorry, I said 40 Newton. Traveling at a speed of 40 meters per second, skid to a halt on wet concrete where the coefficient of kinetic friction was 0.6. How long is the skid? Okay. How long talks about not in terms of time, but in terms of the distance covered. In our test, the final solution was given to be 140 meters. I did not get 140. When I solved, I got 130 something, 136 thereabout. And if we go by the 2-6 rule, that is how it will become 140 for me. But I did not get the exact value 140 meters. Okay. And how many of us got the 140? Can you quickly say it in the chat? If you got 140. Are we still in class? Okay. Great. I got 136 as well. So how did we get our 136? Let's quickly do the summary. We used the equation of motion that says V final, where's number 29, is equal to V initial plus 2A can be S or D, S to mean distance, this is squared. Okay, so the value, this implies the value for the V final, which we said it hot, that it came to a stop, is actually 0 because it stopped. The value for the V initial is given in the question to be 40. Then we have 2 acceleration. How did you get our acceleration? Now, the coefficient of static friction is given. So we got our acceleration from this Newton's second law. Just permit me to use this place. I'll wipe it out. MA. And we'll have that force of kinetic friction is equal to my N. Okay. So the force of kinetic friction is equal to coefficient of kinetic friction times the normal force. So if we put that here, we have coefficient of kinetic friction, normal force, which is always equated to mg, because normal force is acting in response to the weight, equating ma. So this m should take care of this m. Whichever way, if you make a the subject of formula, m will cancel m. So we have dividing both sides by the coefficient of a giving us coefficient of static friction, kinetic friction, and g. So we simply did coefficient of static friction, which is 0.6 given to us, times 9.8 to get 5.88. So that's the value of A we used here. So we used 5.88 and we are looking for D. So we'll solve that out, square this to give you 1600 plus a value for 11.76 D. Okay, is equal to 0. So we have D being equal to, where's my value, 116 over, give me 136 meters. That's how I got my 136. Okay. And I believe that's how most of us got our 136. Do we have a different approach? Is anybody in the class with a different approach? No. Let's proceed to the very last. The very last question is kind of tricky. Okay. I saw several expression of the very last question. And each of our expression had a sense of valid answer. And we don't, it's an even number, so I didn't have the answer in the textbook to compare it with, but I have worked with the rules that applies to what the question demanded to arrive at the answer I want to present. Okay. So if we read through the question, it seems like none of the no parameter is given at all in the question. What do you expect me to do? Okay. We have the dump truck whose bed is made of steel, holds an old steel watering trough. Okay. You note what I'm underlining. I'm underlining the use of the word steel, because they are the lead to what they need, the solution they need from us. So the bed of the truck is slowly raised until the trough begins to slide. What is the acceleration of the trough as it slides down the truck bed? Okay. So to get acceleration, we needed an additional information. Did I jump a question? think I jumped one question. Yeah, 30. Oh, sorry. After that, it's question 30, right? We still have question 31 to go.
Yeah, it's questions 30 and 31. You're on 30.
Oh, okay. I didn't present my solution for 31. I'll just check my book. The class is okay. We'll get to that. So we have a representation of what the description is saying in question 13. Okay. So we have let's picture the truck, then they raise the trough a little so that it slides. Okay. So we'll see the normal force, the friction force, and the weight just before it slides. Now we said that for when we're dealing with friction force and static and kinetic friction, we know that the coefficient of static friction is usually or always greater than the coefficient of kinetic friction. The reason being that the kinetic friction or the static friction, you know, the description we put when you're taking a walk, the surface of the contact is bulging out, and they have the time, because it's static, they have the time to stick to each other to form a higher value of coefficient for that bond. But for the glide, it kind of have just touches or contact. So that is simply the explanation why the coefficient of static friction is usually greater than kinetic friction. So as the question is now, none of the values are given to us. Even when we know that the weight is acting downward, weight is still going to be mg, negative mg. The mass of the truck or mass of the trough is not provided, but they're asking us to find acceleration. So sometimes when we browse through our mind, we might not actually think of a formula to use, but we have one information that was provided to us, that it was raised then just before it glides. That is when we get the acceleration. Then we were treating that problem. We saw that the point where static friction translates to kinetic friction is the point where we experience the maximum force and the maximum acceleration, or the formula for kinetic friction, static friction equals the coefficient of static friction n. Okay, so we will have the max here, where this max, the force become maximum just at the point where it overcomes that static friction. So we have standard value for the static friction of a steel. And the standard value for the static friction of a steel is 0.8. Okay, so our static friction value is 0.8. We even have that information in question 31, where the static friction for steel is given to us, and was it steel or grade? It wasn't specified. We have values for static friction for standard materials. Okay, so if this kind of question is given in an exam or test, usually somewhere either in the formula sheet would have put the value for static friction or kinetic friction coefficient. Okay, so knowing that the value for static friction coefficient for steel is 0.8, let's keep that in mind. Let's continue to the analogy. So we did the free body diagram of the trough on the truck. We see the friction force, we see the normal force, and we see the weight force and the angle of inclination, okay, before the glide. Now, to proceed to calculating our question, we define our coordinate in this system as using the surface of glide as the x coordinate, and then this part acting down as a y coordinate. So that's, sorry, I'm trying to, you see how that's influenced this diagram here now. The forces remained, but the projection on the y-axis will give us an angle that we can actually equate to this angle here, which will help us in the definition of the parameters that we need. Okay, so we have in this kind of expression the total S component of the force and the Y component of the force. All right, so we have in the Y direction the summation of the component of the force. If I have to draw this diagram again, we'll have weight, okay, angle of inclination, then, all right, this is your W, this is your friction force, this is your normal force. So on this Y axis, this is the X, and this is the hypotenuse. So we'll have the Y value being adjacent of our hypotenuse. That is how we got this, okay? This is weight, which is equal to negative G. So the component, we brought out the component of force in the X and the Y component of the motion. So for the S component, we'll have we'll use this one to look at the S component. We define the plane as S component, which gave us the opposite over hypotenuse. Because this is our definition of our S component from the Y and X axis defined. Okay, so in our S component, we'll have just the force of friction in that direction. So we'll have the force opposites, which is the mg adjacent hypotenuse to give us the sine theta. Now, for the S component, where we have the acceleration component, that is why we focused on the S component. Okay, so before the trough began to slide, the force on the Y component are balanced. The friction force is acting in this direction opposite to the motion. So from this equation, M took out M, that is how we got A to be equal to AS, and the S component being equal to sine theta. Now, the angle of inclination is not given, but we'll have the information that the coefficient of static friction is 0.8, which can actually give us the angle. When we have the static friction, we have that tan of the angle to give us the value of this angle. Tan inverse of the static friction, which will give us 38.7 degrees. Okay, so if we know our angle to be, that is the only information we have. We took the tan inverse, we find out our angle, we determine the equation for acceleration as A equal to G sine theta. So we'll have G, which is 9.8 sine 38.7 to give us the acceleration. Okay. So that is the solution for equation 30, for question 30. Do we have alternative opinion? Would you be willing to share? I saw varieties of answers. Really. Any comment on that? Can we proceed? Hello? Am I alone in this class?
Sounds good.
Okay. So for 31, we have the question, which is the very last one. So I have just 18 persons remaining in the class. So thank you for staying by. We still have the videos uploaded as well. Okay. And if you've not submitted your assignment, and I notice that you're just copying what we have in class, don't just copy what we have in class. I'll know that that's just my comment on that. And the rest of you just exit the class without giving a reason to leave. It's okay. But you should, if you have an engagement, because we're using our lab time for this revision. So let's take the very last question and then we'll call it a day. Okay. So the last question says, a 10 kg crate is placed on a horizontal conveyor belt. The materials are such that the coefficient of static friction is equal to 0.5 and the coefficient of kinetic friction is equal to 0.3. The first question says you should draw the free body diagram showing all the forces on the crate if the conveyor belt runs at constant speed. The second one says draw the free body diagram showing all the forces on this crate if the conveyor belt is speeding up. And the last one says, what is the maximum acceleration that the belt can have without the crate slipping? Okay, so we have the crate on a conveyor belt. It's sitting. So at that position of rest, we say it has a static friction, that it's experiencing a static equilibrium because it is what? At rest. All right. And we just need a free body diagram representation. That is just what we need. We don't want any bogus explanation but if you add explanation, because I see also some person adding an explanation to their solution, it's okay. It helps us with how you understood the free body diagram. Okay, so if we want to try to visualize the description, if the conveyor belt is on the horizontal plane, which is defined by the question, we now have like a crate. Let's use this one to represent the crate sitting on the conveyor belt. Now, the conveyor belt, we start moving, which will make this crate to move, right? But the crate appears to also be sitting at the same point while it is in motion. Okay, it's moving. The first question said we should draw the free body diagram. We know the free body diagram using the coordinate system, then the dots representing the crate. So we'll have the normal force acting, and also we'll have the weight acting on it. So these are the forces. We can identify why the crate is at constant speed. Okay, acceleration is 0. If acceleration is 0, net force is 0. Okay. So the second question says, we should draw the free body diagram for when it is speeding up. When it is speeding up and the crate did not slip, because it can move at certain speed, the crate will slip or the crate will fall. But when it's speeding up and the crate did not slip, how will our free body diagram look like? We use the dot to represent it at the coordinate axis, as usual. Don't mind me doing those. Let's make a cleaner diagram. So we'll have also, because the crate is sitting the normal force, then we'll have also the force of gravity on it, which is W, or like some of us wrote the FG. It is speeding up. So we'll have also the friction force, the force of static friction in this direction. Now, some of us drew something like this, and W this way. I also mark it for you because you indicated direction as this way, but it's better to present it like this. Okay, so this is the representation of the free body diagram when the conveyor belt is speeding up. And at the third question says, what will be the acceleration? The conveyor belt is speeding up, so it has acceleration. What maximum acceleration would the conveyor belt have for the crate not to slip? Okay, so we'll have to determine that. That is where the use of all the parameters given to us come into play. If you have comment on, because I also saw different kind of diagram, free body diagram that are different from what we just presented in class. And I'm taking this off because I don't want you to have to change the answer you already plan to provide for this, because some of us who have not submitted our assignment, this solution to this assignment. Okay, so let's proceed to solving the C part, which will be the very last in our revision class today. A maximum acceleration. Let's first bring out the parameters given in the question. We'll have the mass of the crate, M, equal to 10 kg. What other information is provided? We'll have mu x, coefficient of static friction, and we'll have mu k, coefficient of kinetic friction. So we'll have to find the maximum acceleration at which this crate will not slip. Okay. So if we use the Newton's second law, which is equal to ma, the maximum acceleration that this crate will be, A mass will give us the force mass over m. Okay. And what is our maximum force in this case? Before or at that point where the conveyor belt starts moving, we still have the static friction because the crate is still resting on that bed. So we were given two coefficients of friction, but we're not using the coefficient of kinetic friction because it is not, the crate itself is not the one gliding over the conveyor belt surface, but we see the motion. Okay, so we'll be using the value for the coefficient of static friction to solving this problem. So we know the formula for static friction. Okay, so we'll have that, substitute that into this. We have coefficient of static friction and your normal force over your m to give us acceleration maximum. And your normal force is also equal to mg, so you will have mg over m. All right, so m takes out m, so you will have the maximum acceleration to be coefficient of static friction times your g. So we'll have straight out what our g is 9.8 coefficient of static friction multiplied by 9.8 to give us the acceleration of this value. So that is the maximum acceleration that the crate will have, the conveyor belt will have for the crate not to slip. If it goes above that, the possibility of the conveyor belt slipping increases, okay? Which will now bring into play the coefficient of kinetic friction. Do we have comments? I'm expecting us to comment on each of the solutions we display in class today. Come to the
Yeah.
mic to make your comment, yes?
It looks good. I don't know.
Yeah, that's what I had.
Okay. All right. I saw several solutions and several ways we explained that. If you have maybe a personal question on this and you don't want to come to the mic to talk now, feel free to send me a mail. We can organize Zoom meeting for now. And also we can meet in class when the time is right for us to meet, okay? Okay, apart from this, do you have any other question on the topic discussed so far in class? And maybe comments? Some person sent me a mail again asking what should the test 2 cover? It's going to cover a discussion from the end of test 1. And that is the beginning of 5, yeah? Chapter 5 is included. I'll check. No, the test 1 covered 1 to 5. So, right?
Yeah, it should just be 6, 7, 8, 9 on this test.
Yeah, 6, 7, 8, 9, and the early part of 10. Because we'll be having a class on Friday, which is on the 5th, and that is the early part of chapter 10. Okay? So 6, 7, 8, 9, then the early part of chapter 10. Okay? And you should practice the assignment given is part of it, the notes in class, some of the examples that will tell you to check out. See as the example this to buttress this point. Check those examples as well. What else? Do the knowledge check. Those knowledge check parts where we'll have to like do a classwork on what we learned. And what else should it cover? I think that's about all. It's not going to be something to fear, but you just have to prepare as well. Okay. Is that all I want to say? Should we call it a day here?
Yeah, I think so. I think that was good. Like, and we can always go and review the lectures too, which is good.
Yes. So by Friday, if not before closing on Friday, it will be in the morning on Saturday. I'll put up the solution 4-5, the video, that is the slide, because by Friday, when we'll be taking the revision class, I expect everybody to have dropped their assignment. I'll present this more in a slide form, question and answer following each other with comments. I'll put that up on Moodle. I'll also put up the solution and video lecture for assignment 8. And I didn't give assignment for assignment 9. I want you to be preparing for your test. So that's slides, all right? But if I have any question I'd like you to practice, I'll just make comment on that. Okay.
I just want to double check. So the midterm is on the Wednesday, right? The 17th.
Yes, Wednesday the 17th.
Okay.
But
And I just want to double check what time. I
the,
just want to check.
the class time,
Okay.
the usual class time.
So
it's-
not the lab time, just the class time.
yes, just the class time. There's
Okay.
probably going to be lab, but once I confirm that, I'll let us know.
Okay.
Okay.
Thanks.
Thank you. Okay, do we have any other comments? No other comment, then it's a day. Thank you so much for staying to this time. Have a great day. All right, bye-bye.
All right. Thank you. Bye.